Good morning. For the record, my name is Paul Gershevsky. I am the Director of Safety and Licensing for the Nuclear Waste Management Organization. Today I will give a summary presentation on OPG's response to EIS 13514 on waste inventory. I will also comment on some other claims that have been made recently with respect to the DGR safety assessment. In this presentation, I will cover the following topics: the information request, the basis for the reference inventory, including the important radionuclides, OPG's waste inventory verification plan, the safety implications of recent changes to the inventory, and the safety implications of pressure tube waste and ion exchange resins in response to recent public comments. A key point we will make is that the 2010 DGR reference inventory provided a comprehensive preliminary estimate of all radionuclides of potential importance while emphasizing the most important radionuclides. It recognized that there were uncertainties. These were accounted for in part through sensitivity cases presented in the preliminary safety report. Furthermore, while the amount of some radionuclides in some waste streams were underestimated compared with current estimates, these are less important radionuclides in terms of potential impacts. There is no change in the overall safety case. Earlier this year, Dr. Greening identified several potential issues with respect to the radionuclide inventories used in the 2010 DGR reference inventory report. These were with respect to pressure tubes and garter springs. OPG considered these comments seriously and provided a detailed response. In this response, we indicated that the inventory values questioned were estimates and were being addressed as part of OPG's ongoing waste characterization program. We also noted that these particular inventory changes were not significant to the safety case. Subsequently, in the information request, the panel asked OPG to repeat the relevant safety analyses using the revised inventories in order to quantify the effects on the safety case. The panel also asked OPG to provide more details on its waste characterization program in general and on how resins would be measured in particular. This is provided in a waste inventory verification plan. Our response to the information request addressed these topics. This summer, Dr. Greening has made further claims to the panel with respect to the ignition of pressure tube waste and the behavior of ion exchange resins. We will also address these claims in this presentation. The DGR reference inventory documents the total projected inventory within the DGR. About half of the total waste are already in storage at the Western Waste Management Facility. As the rest of the waste does not yet exist, its inventory cannot be directly measured. It must be estimated using OPG system plans, calculations, and other information. The first version of the reference inventory was released in 2008. The subsequent 2010 version of this report was used as the basis for the current site preparation and construction license application. As new data becomes available, we assess its significance. If not significant, we accumulate it for future revisions of the inventory report. The reference inventory will be updated to support the first operating license application. This would be required before any waste could be placed in the DGR. The reference inventory would be further updated in support of the renewal of the operating license. The reference inventory builds on the results of OPG's waste characterization program. OPG's fleet of CANDU reactors generates a number of distinct but relatively well-defined waste types. We presently consider over 25 different main waste types, from incinerator ash to steam generators. The characterization of these waste types considers the data needed for station operation, handling and storage at the Western Waste Management Facility, emplacement in the DGR, and long-term safety in the DGR. A key factor in these different data needs is the time frame. For example, station operation interests include short-lived radionuclides, but these are not important to the DGR since they would already have decayed. We have identified about 50 radionuclides of potential interest to the DGR, considering both operations and long-term safety. The reference inventory is based on measurements or estimates for all these radionuclides. For the DGR reference inventory, we recognized that there were uncertainties. These were to be addressed through the ongoing OPG waste characterization program. For the 2010 inventory report, we particularly focused our attention on those radionuclides with the greatest potential impact on DGR safety. Slide 6 shows the future waste volume predictions from the 2010 DGR reference inventory report. These figures show the projected volumes for low-level waste and for intermediate-level waste on the left and right, respectively. The figures cover the period from 2009 to 2054, when the current fleet of reactors is projected to shut down. The different colors represent different types of waste. In the left figure, looking forward over the next 40 years, the low-level waste is expected to steadily increase with time while the nuclear stations continue to operate. About half of the projected total low-level waste is currently in storage. The blue area in that figure corresponds to non-processable low-level waste. The right figure shows that some intermediate-level waste is generated at a steady rate as the reactors operate, while some is largely produced over the next decade. That is the gray area in this figure, and it refers to retube wastes. Most reactor retubing will be completed over the next decade. Overall, these figures show that there is a reasonable basis now to project future total waste inventories, and at the time of an application for a DGR operating license in several years, a significant amount of refurbishment waste will also be available to support an enhanced estimate of the radionuclide inventory in retube wastes. As noted before, OPG has an ongoing multi-year waste characterization program to improve the basis for our waste inventory projections. The program addresses all potentially relevant radionuclides and waste types. It includes characterization of physical content, notably metals and organics, which is relevant to gas generation. OPG has provided to the Joint Review Panel a waste inventory verification plan. This describes the graded approach used with respect to the amount of data needed, which depends on the importance of the radionuclide and the waste type. Verification of the information is provided in part through use of accredited laboratories. These laboratories routinely calibrate their instruments against standards. The results are also verified through comparison with other published data, interlaboratory comparisons, and a planned third-party review. This information will be available in time to prepare an updated reference inventory. This, together with any other relevant information, would be used to update the safety analysis for an operating license application several years from now. This figure illustrates the main elements of the waste inventory verification plan. As shown at the top of the figure, the core of the program is the ongoing sampling and measurement of waste. Current 2014 work, for example, includes analysis of various low-level waste bins and of pressure tube samples, and an interlaboratory comparison. The next several years will include continued work on both low and intermediate level waste, with priorities guided by the waste inventory verification plan. An interlaboratory comparison will be carried out every few years. During this period, there will also be a third-party review of the waste characterization program and its results. Around 2021, the data would be used to prepare an updated reference inventory to support an application for an operating license. As noted in previous slides, OPG's waste characterization program's objective is to have data on all potentially relevant radionuclides. However, it is useful to understand which data is most important. Slide 9 illustrates which radionuclides are key to long-term safety. This figure shows the maximum calculated dose under several normal and disruptive scenarios. Note that the scale is logarithmic. Each horizontal division represents a factor of 1,000 in dose. The results include all waste streams and all relevant radionuclides. The figure is labeled to show the contribution of the two radionuclides contributing the most to the maximum dose. Other radionuclides contribute smaller amounts and are not labeled. The figure shows that there are only a small number of radionuclides that are very important to dose impact. Under normal evolution scenarios, iodine-129 is important. The higher dose scenarios are dominated by carbon-14, niobium-94, and zirconium-93. These are important in part because of the amount that are present in the wastes and also because of their relatively long half-lives. The figure also shows that large uncertainties in the inventory of many other radionuclides would have no material impact on the long-term safety case. This applies to tritium, for example, which does not appear as an important contributor to maximum dose in any of the long-term scenarios. Of course, we want to have a good inventory for all radionuclides, but understanding the potential contribution of each radionuclide helps set priorities. Slide 10 describes the basis for the inventories of the key radionuclides for long-term safety. Carbon-14 is primarily produced by neutron interaction with moderator heavy water. The corresponding waste streams in the DGR will be the moderator resins. We project the total amount of carbon-14 in the DGR based on measurements of carbon-14 in resins. Niobium-94 is primarily produced by neutron activation of pressure tubes. For the DGR, the inventory is based on activation calculations to the projected end-of-life exposure of the pressure tubes. The calculations have been validated against measurements of niobium-94 in pressure tubes. Earlier this year, Dr. Greening challenged the projected DGR inventory of niobium-94 in pressure tubes. However, the basis for his concern was not correct. Our values are in fact consistent with the data that he was using. Zirconium-93 is another key radionuclide that, like niobium-94, is primarily produced by neutron activation of pressure tubes. It is a harder radionuclide to measure, in part because of its long half-life, and accordingly, we used indirect measurements to validate our calculations. But we are confident of the calculations, and we currently have work underway to provide direct validation. In this slide 11, we focus on pressure tubes. This is the waste form that was questioned by Dr. Greening in letters to the panel. This is a waste that is produced during the midlife retubing of CANDU reactors and also during decommissioning. The pressure tubes are the main source of the key radionuclides zirconium-93 and niobium-94. It is also an important source of other radionuclides including carbon-14, chlorine-36, and curium-244. The 2010 reference inventory assumed retube waste from 16 reactors. This will largely occur over the next 10 years. Most of these reactors have not yet been retubed. So the bulk of this waste had yet to be produced, and an estimate was needed for the DGR. The projected DGR inventory for pressure tubes was based on calculations for bulk activation radionuclides and an estimate for surface-based radionuclides. The bulk activation radionuclides were considered to be the most important in terms of potential dose impact and also to be appropriately calculated, as noted in the previous slide. The surface-based radionuclides were considered less important and were estimated at that time. As noted by Dr. Greening, the amounts of tritium, cesium-137, and curium-244 were significantly underestimated. However, as explained in slide 9, these are not important contributors to post-closure dose. In 2010, OPG had already identified the pressure tube inventory as an area for improvement. We have collected data from prior measurements, and we have specifically acquired additional samples which are currently under study. Another topic that was addressed in this information request was the treatment of the spacers placed between the pressure tube and calandria tubes, also referred to as garter springs. Spacers were made from a zirconium alloy for the first 15 reactors and subsequently from an Inconel alloy. The radioactivity of spacers was not included in the 2010 reference inventory. In terms of the total amount of zirconium in the reference inventory, these are small items, about 50 grams per each 61,000 gram pressure tube. The radioactivity in the zirconium alloy spacers is small compared to that in the pressure tubes. However, the radioactivity in Inconel spacers is high due to its nickel content and is important to the total DGR radioactivity for some nickel radioisotopes. For this information request, the safety analysis conservatively assumed Inconel spacers were used in all reactors. The results show that the addition of this radioactivity does not affect the conclusions of the safety case. Nonetheless, spacer radioactivity will be included in subsequent versions of the reference inventory. Slide 13 summarizes the relevance of the revised pressure tube inventories on operational safety for the DGR. First, there is no change to the normal emissions from the DGR, as the retube waste containers holding the pressure tubes are sealed before arrival at the DGR. Second, while there are higher inventories of some gamma emitters in the waste, all waste packages must meet OPG acceptance criteria, and OPG will operate so as to keep worker exposure below its dose targets. Finally, with respect to accidents, it is first noted that breach of the retube containers is a very unlikely accident due to the container robustness. However, in the event of a breach, there would be higher dose consequences, but they would remain well below public dose criteria. In response to this information request, all post-closure assessment level cases were recalculated to check the effect of the changes to radionuclide inventory in pressure tubes. The results are shown here, with the revised results in the white bars. The revised inventory has very little effect on calculated maximum dose rates. This is because, first, the inventory of only 4 radionuclides are increased by more than 10%, and second, none of these radionuclides or their progeny are important contributors to dose in the DGR. The post-closure impacts remain well below criteria. Dr. Greening has claimed that the ignition of zirconium is an important factor to consider in pressure tube waste safety under accident or malevolent act conditions. It is correct that zirconium can spontaneously ignite under certain conditions, notably if it is in powder form. This is a recognized hazard and safely managed where it occurs within OPG. However, the OPG zirconium retube wastes are in coupons similar to those shown in the top right photo. These are too large for spontaneous ignition. The same report that was used to claim combustibility in fact provides information that indicates these OPG pieces would not spontaneously ignite. And the very small amount of cuttings generated during cutting the retube waste into coupons would be well dispersed within these larger pieces. This is also consistent with decades of Canadian experience working with pressure tubes. I would like to run a short video in which a pressure tube coupon was heated to 1100 degrees C and did not burn.
The sample is now approximately 1,100 degrees Celsius. We'll hold this temperature for approximately 30 seconds. As you can see, the sample glows white with heat but does not ignite. It has been 30 seconds. We'll now let the sample cool down.
This demonstrates that these wastes, consistent with the literature, do not spontaneously ignite at room temperature. Furthermore, in the DGR, this material is also in sealed containers where there is limited oxygen, and the containers themselves are robust steel and concrete containers weighing over 26 tons. These containers provide a very high level of safety. Some of the claims are with respect to risk under malevolent accidents. These claims are not correct because they essentially ignore the presence of the 26-ton container. For security reasons, I cannot discuss malevolent acts in any detail. Furthermore, in placing these wastes within a closed repository provides safe and secure protection from accidents and malevolent acts. Dr. Greening has also recently commented on the safety of ion exchange resins. He first commented on the smoke from resin fires. He specifically commented on some technical aspects of an interim 2009 safety analysis. However, the claim misstates our analysis and conclusions. In our analysis, the impacts of conventional hazardous species in smoke were considered. Carbon monoxide and benzene were selected for this analysis, while explicitly recognizing that smoke contains many other species. The analysis results confirmed the expected conclusion that smoke itself is hazardous. For the final safety report, therefore, we did not see a need to conduct a more accurate analysis of the smoke chemical content. We concentrated on whether the radioactivity that could be in resin smoke was itself significant or not. From a design perspective, our response has always been to work to prevent and mitigate fires. Dr. Greening has also claimed that the DGR safety assessment does not consider the flammable gases that could be produced from resin waste degradation. This is not correct. The possible presence of flammable gases is recognized in our underground design. This is a key reason for our continued ventilation of the underground emplacement rooms, for the monitoring of underground air for flammable gases, until the eventual installation of closure walls on panels. In summary, the DGR reference inventory was a best estimate as of 2010. It was a preliminary estimate, recognizing that we were seeking a site preparation and construction license. The 2010 reference inventory appropriately estimated the key radionuclides. The other radionuclide uncertainties have little or no impact on the safety case, as was shown in the information request response. However, OPG recognizes that it is important to get all the inventories as accurate as possible. OPG has a waste characterization program that is improving the database. Updated inventories would be used for a future operating license application before any waste could be emplaced. OPG stands by its safety assessment. The pressure tube wastes in their packages are not spontaneously combustible. The wastes are safe to handle and store. Placing the waste packages within the DGR will improve the long-term safety. This concludes our presentation. We'd be pleased to answer any questions you may have.